Now we'll move to our next part of our class. I now want to do a couple examples using Newton-Euler equations. These examples are going to emphasize the Euler rotational equations. I've got mini thumbnail sketches up here, the two examples that I want to do first, I want to do now. We'll work through these part way. Ideally we'll get them done. If I don't quite get them done, I do want to stop for a minute and look at a little MATLAB as well. All right, examples. And then Thursday, frankly, is going to be an all example day. This is all the theory that I have to share with you on Newton-Euler equations. So it'll be examples from here on out. I don't think I have these examples in the pre-recorded notes. These will be fresh. So my first example is going to be a piece of rotating machinery. So I've got this major shaft. It's rotating, contained in bearings here. Meant to be a little cross-sectional view of some bearings in your piece of equipment. Rotating along. I'm going to apply some global frame here, N1, N2, and then that would put coming out of the board somehow here, N3. It's funny, I'm kind of drawing it like 2D, but there I've made it look like 3D. That N3 will be coming out of the board. It is a 3D problem, but I've drawn it in 2D. Now on this piece of rotating equipment, I'm going to show some imbalance, or I guess this could be part of the machine. I guess it could be part of the machinery, or you could consider an imbalance. Anyhow, coming off at some angle, I've got this little mass set, okay? So I've got a little rod of length L, and it's rotated at some angle phi. This is fixed. For this example, this angle will be fixed. And my machinery is rotating around this N1 axis by some theta, theta dot, and theta double dot. And here I have bearings. These are my two bearings. So my question is, for this problem, I want to solve for the forces. I want to solve the forces in my bearings under some, under some motion. Or at the end, we might take a moment and say, well, what if I was driving this with a particular torque? What would be the forces in my bearings? Okay. So, here I have a dynamics problem, so I'm going to set the thing up. Let me first assign a body fixed frame. So the first thing I'm going to do is assign, I've got this inertial frame. So I'm going to assign other axes. Notice I've got a rotation around it looks like first I've got a rotation around the N1 axis. So, I said it's useful to maybe write rotation matrices for each of the intermediate frames. So it looks like first I get a rotation around the one axis by this theta. So let me insert an intermediate axis, and I'm going to make it be red. So I get a little, and I'll call it A. So I get a little A1, a little hard to see here, but a little A2, a little A3. Trying to draw it, rotate it just the smallest amount. And then I've got a second rotation, which is that my rod, now this is fixed, but I think it's going to be convenient because I want to be in these body fixed frame. So I get a second rotation around this A3 axis by phi, and that will put my frame, my body fixed frame up here. So I get a B1, I have a B2, and then a B3. And this gives me a body fixed frame, and you can see that my body fixed frame is, attached to this rotating piece of machinery. And furthermore, I've selected B's along these symmetric axes, which is going to tell me that my B's are going to be principal directions as well. So that's handy. So I'm now ready to start my problem. To start my problem, I'm going to need a free body diagram, and I'm going to need the accelerations. I'm going to need to get my, I'm going to have to write my Euler rotational equations, which means I have to write the velocities and the accelerations. For my free body diagram, I'll probably come back to that. At this point, though, I can see my body. I could have gravity acting on it. I'm going to assume at this point that the thing is spinning very fast, so G is negligible in this particular problem. Negligible. So on my free body diagram, I'll have forces acting here. Presumably there's some force keeping it from sliding this way. And my bearings, that's what my bearings do. No moments, the fact that I have the two bearings resist the rotation. So I'm not going to draw those in because they're redundant. Next, so I've done my free body diagram right on top of that thing. Kind of sloppy, but it's there. Next, I want to write my angular velocity, my angular acceleration. So I need to write my angular velocity of frame B with respect to n. And I can see that first I get a theta dot, and that's going to be around the n1 or the a1 direction. And then I get a phi dot, and that looks like it's around the a3 or the b3 direction. So I'm going to try to end up in the b frame coordinates. And I also said that b was constant, so that term's going to go to 0. So it looks like my angular velocity b to n is just a theta dot a1. Easy, I chose an easy example for me to work out here. Nice one to get started. Now I'm also going to need the rotations. So let's take a moment and do those so we have them. I've got a rotation that's going to project me from A back to N, and I need a rotation that projects me from B to A. And then finally, that'll give me I'll get a rotation from B back to N. I'll get those three. The rotation from the A back to the N, it's a projection of, frame A on N. It's a rotation around the one axis by theta. So that's 1, 1, 0, 0 in the first row and column. Cos theta minus sine theta, cos theta. I'm writing kind of small there. Please let me know if that gets too small. Just as an aside, I'm going to take a brief second. Do you have a way to raise a hand? Never thought about that. Well, don't take time to look now. Later on, we may look and see if there's a way to raise a hand, or just shout out. That's fine. The rotation around the projection from B to A, that was a rotation around the 3 by a phi. Rotation around the 3 by a phi is going to give me cos phi, negative sine phi 0, sine phi, cos phi 0, 0, 0, 1. And then finally, the projection from B back to N, it's an Euler set, moving axis set, so I get first this, then this, so I got to multiply R A to N times R B to A. You can see the A's cancel, and that will give me the multiplication of these two, so I get cos phi, negative sine phi 0, cos theta, sine phi, cos theta, cos phi, negative sine theta, and sine theta, sine phi, sine theta, cos phi, and cos theta. All right, if I need rotations, there I have them. And actually, do I need them now? Not yet. So let's go to the next step. I could write the angular, okay, so I'm going to need to do that, but I want to practice writing the angular velocity a couple times here. So let's, oh, this one's kind of interesting. Let's now get the angular acceleration, alpha beta n, which, alpha beta n, which is the time derivative of omega beta n. And it's currently in A-frame coordinates, so I'm first going to take the derivative in the A-frame coordinates, plus the angular velocity of frame A relative to n crossed with this vector, theta dot A1. I'm doing it this way to just practice doing the derivative. You could have expressed this, well, you would do the same thing. You could express it in the B-frame coordinates and do the same thing there. The derivative of this thing in the A-frame coordinates gives me a theta double dot in the A1. The angular velocity of A to n is this thing. This is the angular velocity of A to n. This is the angular velocity of B to A. Now the way we wrote those out. So that is theta dot in the A1, crossed with theta dot in the A1. Those are the same vectors, so this whole thing goes to 0. But that would be the term that I'd have to write out. Now I'm going to write the angular velocity of B to n, but I'm going to write it in B-frame coordinates. So I need to pre-multiply this thing with a projection from the A back to the B. I have a projection of the B onto the A, so I'll take the transpose of this thing times theta double dot A1. So I'll write out my transpose of this guy. That gives me cos phi, negative sine phi 0, sine phi, cos phi 0, 0, 0, 1, times theta double dot 0, 0. And that gives me cos phi, theta double dot, negative sine phi, theta double dot, and 0. That's my angular acceleration. And that's in the B-frame coordinates. Now, I'm almost ready to write my Euler's rotational equations. I need my i's. So my I in the B-frame coordinate about the centroid, and the centroid's here. I'm going to get an I about the B1, an I about the B2, and an I about the B3. I can see the I about the B1. This is a point mass located on axis 1, so I about the B1 is going to be 0. I about the 1 axis is going to be 0. I about the 2 and 3 are going to be equal, and they will be mass times length squared. I've got 2 of those. So I about the 1, 1 is 0. I about the 2, 2 is mass times length squared. That length was L. And I've got 2 of those things. That's I3, 3. And these are about the B-frame coordinates. These are the principal axes. Principal, I guess we've decided it's principal that way, axes, such that my I12, I13, I23 are all 0. So that means that I can now go to my Euler's rotational equations and write them out. Now, I'm going to jump over, just take a second, jump over our notes to see that we wrote it a couple ways. Jump over here. Notice we wrote it a couple ways. For principal inertias, we wrote it out explicitly like this here. And we did have it in the general case here. I'm going to go ahead and write it out for the general case this first time, just as a little practice viewing that. So we said it was, M is about the centroid, that's what we're summing moments about, is I alpha, that's a I about the centroid in B-frame coordinates, that's in B-frame coordinates, plus omega cross I omega. And we have all those little caveats that I've added. So my I is 0 to ml squared to ml squared. Oops. My alpha is cos phi theta double dot, negative sine phi theta double dot, and 0. Then I've got my omega cross I omega. Now, I didn't fully expand out my omega. Here's my omega. omega b to n. That's currently in A frame coordinates. I need to pre-multiply by the rotation transpose to get it into B frame coordinates. And I can see that I'm going to get, to speed things up a little bit here, I can see that I'm going to get a cos phi theta dot, a minus sine phi theta dot, and 0. Crossed again with this diagonal. Times c phi theta dot, negative c phi theta dot, and 0. Now I'm doing a little extra work here. We already had this expanded out for the principal I, but I think we can see this okay. So the first term, straightforward to 0. This first guy is going to be 0, 2ml squared times negative sine phi theta double dot, and then 0. That's the first term. Second term, probably should do this in 2 steps. Cos phi theta dot, negative sine phi theta dot, 0, crossed with, now I need to multiply these 2 guys, so I get 0, negative 2ml squared sine phi theta dot, and 0. Need to do the cross product, so I get an x, cross a y is a z, get minus 2ml squared sine phi cos phi theta dot squared. It's in my z term. I get a y cross a y is 0 and a z cross, so that's all I get. And here I get 0 minus 2ml squared sine phi theta double dot, 0. And finally, the answer. M1, M2, M3 is 0 minus 2ml squared sine phi theta double dot minus 2ml squared sine phi cos phi theta dot squared. And from our free body diagram, we had those F1, F2. So, you know, actually the problem wasn't, you would just, you know, do your equations of equilibrium to go from these moments to the forces. At this point, I want to stop with the moments because I think they make as much sense as anything. So my bearings have to support, notice this. Okay, actually, this is important. Let's go through what I just thought for a moment. All right. You know what? I almost made a little mistake. I should probably write this out so we'll make our mistake more obvious. Remember, this is in the body frame coordinates, P. So these are in the body frame coordinates. I almost said, look, M1 is 0. So I jumped up to this problem and said, that means it takes no moment to drive this thing with some angular acceleration. Well, clearly that's wrong, right? But that's not what we're saying. We're saying M1 about the B1 direction is 0. So there's no moment around the B1 axis. And then I get these moments around the B2 and the B3 axes that are shown here. Probably makes more sense in this example that I want the moments about the end frame, about my inertial frame. To get that, I have to pre-multiply this set of moments by the projection from the B frame to the end frame, which I have above. Scoot that out. Oh, that wasn't very useful. Try that one more time. Huh. Sure, I'm not copying that. Well, that's not copying for whatever reason. I've got the answer here. In the interest of time, you can do that multiplication. When you write this out, you'll see you get a 2mb squared sine squared phi theta double dot, not BL. You get a 2ml squared sine phi cos phi times a theta dot squared sine theta minus a theta double dot cos theta, and you get a minus 2ml squared sine phi cos phi theta double dot sine theta minus theta dot squared cos theta. So these are your moments. The first one is a little bit apparent. The first one is just the angular acceleration, and I had to get my my inertia term projected into the body fixed frame. That would be kind of obvious. The other two would not be that obvious. I don't know that you could readily see those. It fell right out of the Euler rotational equations. We can see that this moment M1 just drives the system. M2 is this term, and we can see it's a depending on the velocity and the acceleration, it's kind of a term that's wanting to straighten the whole thing out. It's kind of pulling on the bar that way, depending on your angular acceleration. And then you get the equivalent thing in the other dimension. Okay. So you can kind of see M2, M3. Get a handle on at least some intuition on how these things are driving, but this gives us the moments to solve each of these. All right, I would like to say another quick word about this problem, and that is I've got these equations, and these are my equations of motion. In this case, I set it up where I said given a particular motion, in other words, given the position, the velocity, the acceleration, solve for the moments, and we can do this at any time. Also, we should notice, by the way, are these things steady? No, these things are going to oscillate. I think that might be even more important. These terms oscillate as a function of theta. So this term is going to be times the sine theta, this term's the cosine theta, even for steady, Dr.
Canfield?
Yes.
Sorry to interrupt again. Would you mind, we're still trying to copy what you had written above. Would you mind scrolling up just a little bit?
No, let me scroll up and then give everyone a minute to catch up because we're at the end.
Yes, thank you.
You want me to go up a little farther?
Yes. Okay.
Okay, I'm gonna let you guys copy that for a moment.
All right, thank you.
There's two other points I want to make about this problem. For a steady rotation, for a steady theta double dot, for example, that means your theta dot's going to grow. Or if you had a 0 theta double dot, then that would mean theta dot squared would be constant, or some combination. Probably for rotating machinery, we might assume that theta double dot is constant, conceivably, but you're going to get these sinusoidal terms. So you're going to get a cosine theta term, you're going to get a sine theta term, and you're going to see these in your moments. So you're going to have these driving terms that are going to be sinusoidal inside your moments, and these will give excitations to your system. So for 3D, you see that. We saw that in 2D problems, and here you clearly see it in 3D problems. It's going to happen about all the axes. The other comment that I want to make with this problem is a little more generic for just looking at these dynamics problems. So in this particular case, now I'll assume I set these up. These problems are nonlinear. They're nonlinear in that if I say my theta is my unknown, I'm trying to solve second order differential equation in theta, then I'm going to get cosines and sines. I just always get these. That's where the nonlinears come in. But when I start looking at the unknowns in terms of my accelerations and my moments, they'll always be linear. So in this particular problem, so what I'm trying to say is I'll set these up as linear systems of equations. At this point, my equations of motion is linear in my particular unknowns. In this problem, if I was given the motion and I had my m's, then here would be my linear system of equations. So I just would have some in this case, this is the identity. Maybe I should put a little ident down here. The identity times m equals this right-hand side. Alternatively, what if I said, given some m1 about the n-axis, some m1 about the n, or the just driving torque. Solve the dynamics of this problem. Well, in this case, it's a 1 degree of freedom system. This was a special problem. It's 1 degree of freedom system, which means that I have, my degree of freedom is theta dot and theta double dot, which means I need second order differential equations. And since I'm using Newton-Euler methods, I'm going to get constraints. So if I just write the moment equations, I'm going to get 2 constraints. And in this case, the constraints are going to be the M2 and the M3. That's what constrains the motion per the kinematics I say. So to set this up, I would need to write a matrix that's a function of my unknowns, theta double dot, M2, M3, and then everything else would be on my right-hand side. All the knowns would go over here, the knowns. I'd set it up this way. So if I look back up at the equation above, I would move the theta 2, all the theta double dots, the M2s, the M3s to one side of the equation, and move these guys to the other, and I'd have to write that out. So, it looks like all this stuff will go to the right-hand side. So what might it look like? Well, the first term, would be, that was a point when I wish I had a bigger board. I know it's a little hard to see, but my coefficient of my theta double dot, the first column is going to be, I got to move it to the, let's say if I move it to the left-hand side, negative 2ml squared sine squared phi times theta double dot equals m1. That's now a known right-hand side. The second equation, I got the negative, I'll move it over. So I'm going to get a 2ml squared sine phi cos theta times theta double dot plus 1 times m2 plus 0 times m3 equals the stuff that's left over, that 2ml squared sine phi cos phi theta dot squared sine theta, and so on. So this is then what my equations of motion would look like for that 3 unknowns. I'd be given some driving torque m1, and then presumably, at least instantaneously, I'd have to know the velocities. right? And then I could solve for the acceleration and the other bearing reactions. It would give me a linear set of equations that I could then solve. Versus right-hand side. Of course, you know, again, depends on where you say there's the nonlinearities. If theta is not known, you do have nonlinears in this coefficient, but we assume that we'll solve it in a stepwise fashion, which makes those known. Okay. Questions on this example? Well, at this point, I've run on just a little bit. I've got an example that's much like the first. You know, I'm going to suggest that we hold off on this second example. The homeworks that you're working on are not, the homeworks that you're working on are from just developing rotation operators and then writing velocity acceleration. So I'm going to hold off on our second example till when we get together on Thursday, and I'll introduce a couple more. So we'll try to work 2-3 good examples when we're together. What I would like to do now is a little more MATLAB practice in the last 20 minutes that we have. And again, if there's questions or comments, please raise those. But otherwise, I want to jump to now the MATLAB portion. Just had it there. And there's two examples that I want to do together in MATLAB. I've pulled up, I just opened up MATLAB and it conveniently brought up the last problem that we did together. It was a problem doing symbolic operations. By the way, again, in the homeworks, can use MATLAB if you want to use the symbolic tool or something else, you know, Mathematica, Maple. Yes, you're more than welcome to use those. I'll be using MATLAB from here on out. You know, I've just now kind of focused on this one program mostly, but the others are fine too. You're welcome to use them on your homework. I am expecting that you'll be able to do all these operations by hand first. So just make sure you're comfortable doing the operations by hand, but then jump to MATLAB. Feel free. There's two examples I'd like to set up and see if we can work through. The first one, let this be the problem that we've already solved. So let's set up a Euler's angle equations for a, let's first do the 313 alpha, beta, gamma case. So this will be by, you know, you put down you or me, Steve C. You know, and I just realized as I'm typing this, I don't think I ever put this on. I need to put this on to our website so you have access to these. So let me add to my list of things I need to be sure to do, and that is add this little thing so you can go back to it. I'll do that. I'll make sure I do that before I leave this room today so you have these. And our date is 6/27. You know, we're going to derive Euler's angle equations for this case and others. So that's the problem that I want to set up. I'm going to jump back to our OneNote. We've already done this example by hand in class. Now let's set it up in MATLAB. So here it was. I had the 313 alpha, beta, gamma set. I wrote down the rotation. I wrote down the angular velocity term. That was my first and second steps. And then it was just a matter of doing the math. So at this point, I think I can at this point, I think I can speed up my math since I have the problem set up. I now know conceptually how I want to set the thing up. So, and I'll do this one from scratch one more time so we can talk about it out loud, although I think we've already done it. So the first thing I'm going to do is create, well, the first thing I'm going to do is clear my workspace. I'm always going to do this. It's a good idea to get in the habit of doing that. It helps you avoid errors sometimes that may occur if you have a variable you assume, but you didn't specifically define and it's already in the workspace. I'm going to define my variables. So I'll say sims, and I want alpha, I want beta, I want gamma. I will need a alpha dot, a beta dot. I'll just call it D for dot, and a gamma dot. I may need some others along the way, but I'll stop with those. And I've kind of gotten in the habit of declaring these as reals. If you add real at the end of the sims, it will make all those variables be real. I expect them to be real. In other words, not complex, no imaginary terms. And that's handy in one particular case. When you take the transpose, MATLAB by default always takes the complex conjugate, transpose a complex conjugate, applies that operation. And if you declare them as reals, then it just gives us a transpose the way we expect it to be in our case. So I'll leave it that way. All right, so I need to define the rotation. So my rotation, first I had the rotation from the prime projected on the end frame, which is a rotation around the 3 by alpha. So it was a rotation around the 3 by alpha. So it was a cos alpha space negative sine alpha space 0. Next row, I'll line these things up. A sine alpha space cosine and 0. Not sure why it's not liking. Not sure why it's giving me that little underbar. I'll ignore that though. And then 0, 0, and 1. My projection from my double prime to my prime was a rotation around the 1 axis by beta, so it's 1, 0, 0. I got something like a cos beta negative sine beta 0. And then finally, my rotation from the double prime, excuse me, from B to the double prime, kind of got a goofy notation here, is a rotation around the 3 by gamma. So I get the same thing I did the first time. So cosine gamma, negative sine gamma, 0, sine gamma, cosine gamma, 0, 0, 0, and 1. All right, now I need the angular velocity. So my angular velocity, omega of B to N, angular velocity of B relative to N is alpha dot in the Z prime direction. So I'm going to, if it's not too confusing, I'm going to try to do this all in one big step. So it was first, well, let me think about it. Yeah, let's try one big step. So I had the alpha dot in the Z direction. So it's going to be in that Z prime direction. Alpha dot was basically 0, next row. So I'm going to use a semicolon to get me to the next row. 0 in the, so 0 in the X, 0 in the Y, and then alpha dot in the Z. So that was the first term. The second term was a beta dot in the X. So it was beta dot in the X, next row 0, next row 0. And then the third one was gamma dot in the 3 direction. So it was 0 in the X, 0 in the Y, and gamma dot in the 3 direction. So I have those. So that's my omega b to n. However, this is in the mixed frame coordinates. This is in the prime, and that's in the double prime. So I need to, you know, this one is fine. This one I need to project from the double prime back to the b frame coordinates. And I have b to double prime. So I need to remultiply this guy by rb double prime transpose. Okay, done about a couple things here. We saw in the notes that I had to pre-multiply by the projection that takes me from the double prime to the p, or excuse me, double prime to the b. Here I have the b to the double prime, so I take the transpose of that, and I need the multiplication. This one I have to go from the single prime to the b. I have the single prime to the double prime, and I've got the double prime to the b. I just have to take the transpose of both. So I'm going to first multiply these two. So I needed the r, pp, so the projection from pp to p, by the projection of rb to pp. And I need the transpose of all that. Okay, that was probably marginally helpful, what I did. I know I threw a lot of stuff in there. I think we're okay. I think if we go down and check the notes, compare this with the notes below, I think this is going to match up to what we did. Here I'm just doing it one step. But let's try it. So I'm going to do it one more time. I'm going to do this. I don't think I showed you this before. I may need to simplify. Well, let's see if we can simplify. We'll come back and see if we can simplify. So this is my code. This should give me the angular velocity of v relative to n. I had to do these steps. I'm going to give it a run. I call it an Euler 313. That was fast. I'm going to run it one more time. That was really fast. Didn't expect it to be that fast. And nothing printed the screen, so I'm going to print out to the screen my omega b to n and see what I get. Oops. And I get this, these terms. Let's compare that with what we got in class. So we got a beta dot times cosine gamma for this first term. We got an alpha dot times sine beta sine gamma. That one looks good. We got an alpha dot times cosine gamma times sine beta. That one looks good. A minus sine gamma times beta dot. And then the third term, which is gamma dot plus alpha dot cosine beta. Okay, we get the same answer. And the nice thing is that took a little bit of work, but now I could change up my Euler rotation set and pretty quickly solve for this. The other thing we did was, now that I'm looking at this guy, I'm trying to think about how we can pull out the C matrix here readily. I'm sure there's a way to factor. I don't want to spend time right now trying to find this factor. I would go like, I would look up at the help. I would try to find something. It would take a little bit of time. No, that's not what I'm after. I might be able to find a way to segregate this out. In this case, I'm just going to cheat a little bit and hard code it. So I'm going to now overwrite my omega. And I'm going to say my omega, well, I'm going to write my omega as a C. I'm going to write the C matrix, okay? So the C matrix was this matrix sine, beta, times sine, gamma. I'm sure there's cleaner ways to get this thing actually, because this was the first column. This first column here was the first column of our rotation from first prime back to B or something. At this point, I just want to show one operation to you, so I'm going to type it in kind of longhand. Second term was cosine gamma. Third term was 0. Second row was sine beta times cosine gamma. Second term was minus sine gamma, 0, and then cos beta, 0, 1. Okay, and then what I want is the inverse of C. So I'm going to say the inverse INVC is inverse of C. And I'll print that to the screen. So I'm going to go ahead and run this. And I get this guy down here, a little messy. That is the inverse of C. The reason I wanted that was because I'd written my Euler rotational equations alpha dot beta dot gamma dot as a function of something omega. And I want to see what that is. Right now, C is a little messy. Hopefully you can clean it up. In MATLAB, to clean this thing up, I'll use the simplify command. So I can just do a new line and say simplify inverse C. So I'm just overwriting it. Or I could have just executed the simplify command outside the inverse command. I'll run that, see if I get something more simple. And I do. It simplifies it quite a bit. Simplify works pretty well. It's not perfect, but it does a pretty good job. See, I went from this to this guy. Now I can see this pretty clearly. And then finally, I'm going to do one more step, and that is I'm going to try to write out my Euler angle equations explicitly in terms of my 3 omega terms. So I'm going to add those omega 1, omega 2, omega 3, and I'll make those as real. So down here, I'm going to just write my ANS equals inverse of C times this matrix omega 1, first row, omega 2, second row, omega 3, third row. And I'll print that to the screen. And this is my Euler, this is my result. Right here's my answer. So alpha dot equals omega 2 times this cos gamma divided by sine beta equals plus omega 1 sine gamma divided by sine beta. Beta dot equals omega 1 cos gamma minus omega 2 sine gamma. And then finally, beta 3 or beta dot equals omega 3 minus all this stuff. All right, nice example. I have one more example, and I've got about 2 minutes. The other example is related to this problem, I called it homework, but at this point on the homework, here on the homework, I indicated for this week, do problems 4 and 6. Problem 18 asks you to write a kinematics, we can look at it. Problem 3 asks you to write a write a MATLAB program that'll animate a kinematic model of a box falling off a ledge with a constant angular velocity. So I would like you to draw for me an animation showing a box falling with fixed kinematics. So it's falling. So you choose the rate at which it's falling. Just assume just make up your own kinematics. It can move in any way you want. It's falling, and I want it to be rotating with a constant angular velocity 1 radian per second. I didn't even see what direction, so just choose a direction. That's going to be a little bit of work, and you need a little help getting set up on this. So I think what I would like to do is I really need a little time showing you this. I need to put together a little example. I'm down to 1 minute. I'm going to put together an example that you can watch and see a little more information on how to do this. It will effectively be a way that we can solve dynamics problems, get numerical values, and have a very simplistic visualization of those in MATLAB, because those tools are readily at hand. The tool that I'm going to use is Patch. See if that works. Okay. Our time is officially up, and I'm not going to get anything in the last minute that I've given myself there. So I'm going to create a little I'm going to have to record a little example doing some MATLAB graphics, simple graphics that you can then manipulate with your rotation operators, your angular velocity acceleration operators to see how bodies move and start characterizing that. It's a nice addition, and it's what I want to include in our MATLAB assignment. Okay, so this brings us down to the end, and we're at the end. So let me take any questions you have, and I'll say a concluding word. Questions? Going once, twice. Okay, so I will see everyone Thursday at Oak Ridge. The same room as last time. I'll be at the same room as last time and set up. Hopefully my computer won't be doing an update. Kevin has a room secured for Y12 participants over in, he's got a room. So if you can't make it over, talk to Kevin. Kevin, did you want to say the room again?
Yes, it's in the Jack K Center. It's room S2CO5.
Okay. Kevin will either be here or there. I'm not sure, but on Tuesdays, Kevin's going to be there. So feel free. And I'll see you with your homeworks on Thursday. Okay. Thanks all.
Thank you. We'll see you.